Hello, 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 everybody. Root Beer here. Looking at question number 10 now on the 2005 Euclid contest. This is the very last question. Should be the hardest, although some of the questions before have been a tad trickier, but that's okay. Let's prepare ourselves for question number 10. A school has a row of n open lockers numbered 1 through n. Okay. After arriving at school one day, Josephine starts at the beginning of the row and closes every second locker until reaching the end of the row, as shown in the example below. So there she's closing 2, 4, 6, 8, 10. Okay. Then, on her way back, she closes every second locker that is still open. Okay. So the ones that weren't closed were the odd numbers. She starts coming from this way, so 13, 9, 5, 1. She continues in this manner along the row until only one locker remains open. Define f of n to be the number of the last open locker. For example, if there are 15 lockers, which we've got here, then f of 15 is 11. So if she closes those, then that leaves 3, 7, 11, 15. 7 and 15 go with the next round, and then we finally close 3, leaving just 11. Okay. So, A part, determine f of 50. So this shouldn't be that bad. I usually try and recommend that you guys at least look at something like 10a, just because usually for question 10 what they do is they introduce a brand new concept. They did that here. Some lockers opening, lockers closing. It's not, say, a straight circle geometry style question. There's usually a new definition, and to get you accustomed to that new definition, 10a is usually, I wouldn't say easy, but it's usually a basic computation question. Okay? And if you find yourself with 20 minutes at the end of the contest, and you really don't have anything to do, you know you're not going to get to all of 10, you can still try 10a, because it's likely just reading comprehension. Do you understand how the lockers are closing, and can you write out all 50? That's all it really is. Okay? So usually try 10a, because it's usually just a very quick computation based on the concept that they just introduced. B and C and D are the hard ones, where they really ramp things up. So we're going to try and compute f of 50, and since we're going to try the whole question, while we do f of 50, we're going to take note. What sorts of numbers are left at each stage? Because I think that might be a little key. Okay? Something I've noticed right here is, so take a look at these numbers. So the evens are always going to go away right away. Okay? And then the next round, which one's closed? Well, yeah, 13, 9, 5, and 1. But notice that these numbers differ by 4. And the next numbers closed differ by 8. I think this is important. And I'm not quite sure how, but as we continually close more and more lockers, each pass, the numbers that we close differ by the successive powers of 2. And I think that might help us in some way. I don't quite know how, because I haven't read B and C yet. So let's do that now. So we'll do A first, obviously. But it's a good idea to, in your head, say, okay, where are they going with this? What do we need to be looking out for? So in B, we want to prove that there is no positive integer n such that f of n is 2005. Okay, interesting. And C, prove that there are infinitely many positive integers n such that f of n is f of 2005. Okay, so these two are very similar in their final statement, but you can't have f of n be 2005, but you can have f of n be f of 2005. Will we actually have to compute f of 2005? I hope not, but maybe there's a way to compute f of n just from looking at n. And that's something we might have to figure out. Okay. So, determine f of 50. Well, only one thing to do, and that's go to the notebook and start crossing some things out. Will I be able to get... so let's just say something quickly. Notice on the first pass, we always eliminate, well, not eliminate, we should probably say close the even lockers. So this is actually a proof that you could never have f of n be 2006, but they were specifically asking for 2005, so. I wonder what would happen if you closed every third locker and every second locker and things like that. Anyway, not anything to worry about for right now. Okay, so what are we left with? We'll be coming from this direction, and we're left with 1, 3, just because I don't think I could fit all 50 numbers across here. 17, 19, 21, 23, 25. Okay, we're halfway there. 27, 29, 31, 33, 35, 37, 39, 41, 43, 45, 47, 49. Just made it. Okay. So, on this pass, what do? Well, we skip over 49, we eliminate 47, 43, 39. Let's go down multiples of 4 here. Okay. So then we come back and we skip over 1, but we get rid of 5. No, we don't get rid of 9. Don't get rid of 9. We'll place the 9 back there in just a moment. We get rid of the 13, the 21, the 29, 37, 45. And then we come back at it again. Let's say the orange pass, 49. Then we get rid of 41. Then we'll have to go 16 below that. So the 25. 16 below that gets rid of the 9. Then we'll have sort of the green pass here. So we start with 1 and skip over that, get rid of the 17, close that. Then we'll go up by 32, so that'll close the 49. And finally on the pale yellow pass, we got 33, skip over that, go down by 32 to get the 1. Okay. So that leaves, oops. And if you were writing this up, you'd write it up a little nicer, but this is you'd actually write the numbers out each time, I think. So f of 50 is 33. I don't know, by following the process. So 33 and 50, how do these numbers relate? And we know f of 15 and f of 11. Or, sorry, not f of 15 and f of 11. We know f of 15 is 11. What are we to do? Well, I definitely think powers of 2 will play a role, and maybe some sort of modular arithmetic. Am I certain of how yet? No. So what I'm going to do is I'm going to, if you're stuck like this, so with this question, you can pick n to be anything. Okay, we specifically want to show that you can't have, so we finished A. We want to do B now. We need to show you can't have f of 2005. No, sorry, f of n being equal to 2005. So that's a big number. I'm not about to write all those out. So I'm stuck. What am I going to do? I'm going to investigate smaller cases. Yeah, they just had me do f of 50, and we have the example of f of 15. But those aren't really connected. What I want to do is maybe do something small, something self-contained, like maybe compute the first, I don't know, since I think powers of 2 are important for this one, maybe compute f of the first n's going from 1 to 9 or 1 to 10, something like that. Small numbers so I can quickly do it, and maybe I can generalize and notice a pattern. Okay, so that's what I'm going to do because I'm stuck. Right? I haven't learned what I want to learn from doing f of 50. other than I'm really cemented that powers of 2 might be a thing. Okay, so to investigate, let's compute f of n for n is 1, 2, 3. We're just going to keep going for a while until I notice something. So if I just have 1, obviously f of 1 is equal to 1. Not interesting. 1 and 2, well, we'll cross out the 2, and f of 2 will be equal to 1. How about 1, 2, and 3? Well, we'll cross out the 2, and then on our way back, we'll cross out the 1. So f of 3 is 3. Interesting. 1, 2, 3, 4. So we'll cross out the 2, we'll cross out the 4, and then on our way back, we'll cross out the 1. F of 4 is 3. 1, 2, 3, 4, 5. So cross out the 2, cross out the 4, then we cross out the 3. Don't cross out the 1, but on our way back, we'll cross out the 5. F of 5 is going to be equal to 1. 1, 2, 3, 4, 5, 6. See, we're getting a lot of information, and this isn't taking us particularly long. So I'll cross out the even numbers. Then on our way back over, skip over the 5, get rid of that 3, and then we got the 1, and get rid of that 5. F of 6 is 1. So something I'm certainly noticing is that final even number does not make a difference. Okay? If it's even, so I think f of 2n this is just my current thought. F of 2k is the same as f of 2k minus 1. This is what I'm thinking. So 1, 2, 3, 4, 5, 6, 7. And so we cross out these ones. But now the 7 adds a new wrinkle, so we get the 5, and cross out the 1, and then on our way back we'll cross out the 7. So f of 7 is 3. I'm betting f of 8 will be 3 as well. Why? Because when we cross out the numbers, the even numbers, we're still left with the 1, 3, 5, 7 that we had last time. So we'll still skip over the 7, cancel out the 5 and the 1, and then on our way back get rid of the 7. So we'll get f of 8 is 3. Now I think with f of 9, what might we get? I'm thinking we might get 5 as our final answer. That's what I'm thinking. One, 2, 3, 4, 5, 6, 7, 8, 9. Get rid of those pesky even numbers. And then on our way back, get rid of the 7 and the 3. And then we're left with we skip over the 1. So we go 1, get rid of the 5, keep the 9, and then get rid of the 1 on the way back there. So f of 9 is equal to 9. Okay. So my thought was wrong, and that's okay. I'm not going to bother with 10. I'm fairly certain that I could prove now that f of 10 will just be 9 as well. So let's concentrate on these odd numbers. 1, 4, 6, 8, 10. Because what we want to do now, to show that you can't have 2005, we need to show what sort of numbers could appear as f of n. Okay. So skip over the 11, get rid of the 9, and the 5, and the 1, and then skip over the 3, get rid of the 7, and skip over the 3 and get 11. So f of 11 is 11. Alright, get rid of the even numbers. Then on our way back, 11 gets bonked on the head. 7's gone. 3's gone, and then on our way back, 5 is gone, and 13 is gone, and then on our way back, we skip over, and we get 1, so we get 9. F of 13 is 9, and we know F of 15 is 11. So what is going on? Okay. So wild stab in the dark time, and I'm going to sort of summarize this on the next page here. We're going to ignore the odd numbers for a moment. F of 1 was 1. F of 3 was 3. F of 5 was 1. F of 7 was 3. And F of 9 was 9. F of 11 was 11. F of 13 was 9 again. And F of 15 was 11. So, things I'm noticing is that sort of this is 5, the remainder of 5 when you divide by 4. Okay, and this is the remainder of 7 when you divide by 4. Now, that's because 4 is the most recent power of 2. And this is just because I think powers of 2 might be relevant, so I'm connecting it to powers of 2. So then we get this 9 and this 11, and I don't quite know what's going on there. But then we hit... So this is F of... Actually, no, I don't quite know what I'm saying here, but looks like it's going, like 9 is 8 plus 1, and 11 is 8 plus 3. So I'm wondering if it's multiples of 8 or something. So for example, F of 17, I haven't a clue what it is, but it's another multiple of 8 beyond. So I would guess that this is going to be sort of 16 plus 1. So I'm guessing F of 17 might be 17. And F of 19 might be 19. And I'm guessing F of 21 will be 17 again. I think F of 23 will be 19. And then I'm going to go out on a limb here and say, so this is 16 plus 3, 16 plus 1, 16 plus 3, and then I'm going to say it's going to be 16 plus 9, so F of 25 will be 25. And then 16 plus 11, and then 16 plus 9 again, and 16 plus 11. This is my theory. I don't know if this is true, so I'm going to pick one of these at random and say, is this actually what we've got going on here? So let's try 21. Again, I'm going to skip over the odd numbers. No sense in writing, or not the odd numbers, the even numbers. Going to skip over them. No sense in writing them out. So 21. So now we're on our way back. We skip over the 21. We get rid of 19, 15. And we're on our way back this way. Get rid of the 5, the 13, and the 21. Skip over the 17. Get rid of the 9. Then we're on our way back, and we get rid of the 17. So F of 21 is 1. This is not what I thought was going to happen at all. Not what I thought was going to happen at all. So, what the heck's going on? Well, this just means I need more information. I don't know why after 11 I wrote 21. 13 is what we've got going on here. 13, 15, Let's try 17. So on our way back, get rid of these ones here. Then on our way forward, we get rid of these ones here. On our way back, we get rid of the 9. And then on our way back, get rid of the 17. So f of 17 is 1. Okay. What's f of 19? So we're on our way back. 17's gone, 13's gone, 9's gone, 5's gone, and 1's gone. Then on our way forward, the 7's gone. Nope, the 11 stays. The 15's gone, though. Then on our way back, the 11 goes. And then the 19 goes. So we get 3 here. We should get a 3 here. And I'm going to guess that that's a 9. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25. On our way back, so close these ones. Then 5's gone, 13's gone, 21's gone. We'll close the 17 next, then the 1, and then the 25's gone. So we did get a 9. Okie dokie. So what in the heck is going on here? So what's so special about 9 that when we do 25, it gets left on its own? So, So I'll bet F25 is 11. And then F of, or not 25, 27, F27 should be 11. F of 29 should be 9. F of 31 should be 11. Okay. And we know F of 50 is 11, so I'm going to say F of 49 must be 11 as well. So f of 25, the remainder of it, when we divide by 16, is this f of 9 here. So f of 25 is f of 9. And f of 27, I'm saying, should be f of 11 because they differ by 16. And we can go all the way up to 31, but then we hit another power of 2. And once we hit another power of 2, I guess the cycle starts over again. But then why is f of 9 9 and not 1? Okay, because that's what I would have thought would happen. Right? Because if we notice, we've got f of 1 is 1. And then also f of 3 Why is that not 1? Because the closest power of 2 to 3 is closest power of 3 is 2. So 3 minus 2, shouldn't it be the same as f of 1? Unless it's powers of... Oh, maybe powers of 4 come into it as well. And it's some weird inclusion-exclusion thing. Okay, so new thoughts. New thoughts. So I'm going to say f of 2 to an odd power plus 1 is 2 to that odd power plus 1. This is my thought. So that would explain why f of 3 is 3, and f of 3 is, and f of 9 is 9. But f of 5, which is a power of 2 plus 1, is not 5. It goes back down to 1. And I'm going to now guess f of x plus 2 to an even power is equal to f of x if x is less than 2 to that even power. Does that track? I don't know. Okay. F of 1 is 1. F of 3, well, if we write it in binary, that's going to be, it's 3. But f of 5 written in binary, that's f of 1, 0, 1. And I'm going to say something like, then... So my thinking now is if you write it in binary, only the odd spaces count, otherwise it's 1. So f of 9, that would be 8. And it's 9. But then f of 11 is f of 1, 0, 1, 1, 2. So we're going to say that that's f of 1, 0, 0, 1 plus f of 1, 1, 2. Okay, so this single guy here and this single guy here. I don't know if what I'm saying is coming across because I think I barely understand what I'm trying to get across. If I had something like f of 1, 0, 0, 0, 1, 0, 1, 1, then I would say that that's got, in base 2, by the way, then I would say that this one up here gives us this. And then this one here gives us this. And then this last one here gives us this. That only the odd powers matter. And so that even if I had a 1 here and a 1 here, still wouldn't contribute in any meaningful way. This, I believe, matches with everything we've got, but I haven't a clue as to why this would work. So, here's what I'm going to do. If I think this works, 1, 3, 5, 7, 9, 11. We've never done 31. Now, I predicted a while ago that I thought 31 would be 11. But what I'm going to do is I'm going to use their binary representations and keep track of everything that happens there. Not 26, 27. Like I've been saying from the beginning, I think powers of 2 are key. So we've got 1, we've got 1, 1. We've got 1, 0, 1. I'm writing them upwards-wise. We've got 1, 1, 1. 1, 0, 0, 1. 1, 0, 1, 1. And we've got 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1. And 1, 1, 0, 0, 0. Nope. Need a 1 there. Because the remainders are all, they've all got a 16. So we got the 1s, the 2s, the 4s, the 8s, and now the 16s. So we'll get a 1 here. So 16 plus 5, 16 plus 7, 16 plus 9, 16 plus 11, 105, 111. Okay. So we've eliminated the evens. Evens don't matter anymore. We'll use purple now. We'll come back. We'll cancel out everything that, how are all these numbers in common? Everyone who's got a 0 here just went away. Okay. Now we're coming back with the orange, and now it's going to be everyone who's got a 1 here. If they weren't already gone, they are now. And now we'll come back at it with the blue. So the 27 is gone. And now it's everyone who's got a 1 here. No, the 27 is not gone. It's not gone. So it'll be 27 minus 8. So this 1 will turn into a 0. And so it's everybody who's got a 0 here. Will be gone if you're not already gone. So the 19 and then the 3. So we'll add this 27 back in really quickly. And now the green pass. We're coming at it from the 16s. We skip over 11. So then we go up to 21. And now it'll be everyone who's got a 1 here. If they weren't already gone, they are now. Okay, because if there were more, we'd add 16. And then this 1 bit would change to a 0. And so he would stay. And then the next one, we'd add another 16, so this 1 would be back. Okay. So that certainly, I would say binary definitely clarified a bunch of stuff. Hasn't clarified enough for me to be able to start saying, this is gone, this is gone, this is okay, this is... Okay, because what I've really had on the previous page with my sort of f of this binary should be f of this binary plus this binary plus this binary, it sort of was just wild guesses to fit how much we'd already worked out. Okay, so f of 31 is 11. Great, that's what I predicted. But why? Okay, is it for the reasons that I thought? Does this break down in terms of your binary representation and then the odd position ones just sort of split off? Or is there something else going on here? I don't know. Okay, so if we were to do this all in binary, evens are gone first. So binary with 0 in one's digit, or units, is gone. Okay? So that's true. And then on our next pass, we care about the tens digit. So the second place, the 2's. And what do we do? Well, whatever the first one we encounter is, which would be the highest odd number less than the n that we started with, that'll be whatever that bit is, whatever that digit is, it'll be the opposite one. So here it was the 1's, so we got rid of all the 0's. Had we been looking at 29's, we would have gotten rid of all the ones with 1's. So how do we want to say this? Here the zeros went because we had 31, but if we had 29, we would have had a 0 there, so all the ones with 1's would have gone. If we'd had 27, all the ones with 0's would still be gone. But how does what we cross relate to n? How does what we cross out relate to n? That's the question. Because if I could relate it to, say, the binary representation of n, then I think we'd all be set. Because wouldn't it be possible if we did say 30, and we had this 29 here, we'd cross out all the ones with 1, wouldn't that sort of leave 5 as a possibility? Couldn't f possibly give us 5? There's got to be some way to rule this 5 out. Let's leave the second digit aside for a moment. When we come back down here for the 4's, we're either looking at 1 or 3 left. Both of them have 0's, and that's why the 4's, you'll never have something that has a 4 in it. Your binary representation, if you've got a 1 where the 4 is, you're screwed. And then again, when we come back down to 16, or when we start this way, we're going with 16's. Now, the first thing we encounter that's left in the list, it'll have to be something that had 0 there. So the next thing we go to, say this 27 here, it'll have a 1, and the 1's will be the ones that we cancel out. So you'll never have a 16 there either. Fantastic. Okay, so that's a reason why we can do that. But you can have, for example, a 0 in your 2's digit. You just could never have 5 because it's got a 1 here. Okay. So that, I think that's enough information to get rid of 2005. Okay? We have to write this up, and I will. But I'm still just investigating. But that's enough information, I think, to get rid of 2005. Okay? Because its binary representation will probably have like a 4 or a 16 or 64 would also mess up. But then, now I'm thinking about C. Do I have enough information to tackle C? Because if I don't, while I'm investigating, I should be investigating. Do I have enough information to tackle C? And that would be showing that whatever f of 2005 is, it has to occur multiple times. I'd have to be able to prove that that's going to happen a lot. And I think maybe if we investigate just a teeny bit more, we might be able to. Because we've seen that 3 comes up a lot, and 9 comes up a lot. And I think we can predict ways that this will happen. So, for example, 25 also gives us a 9. Why is that? Because when you do your 16 pass, everything 16 and above goes away. And that includes our dear friend 25 here. And so it'll have to be 9. Well, it doesn't have to be 9 at that point, but my point is the 25s, like 17, everything 17, 19, all of them will have to have gone away. We'd have to prove that a little bit, but why would that necessarily leave 9? I don't quite know yet. Okay, I think we still need to make a connection between the binary representation of n and the actual outcome, and the actual output number. Okay. Yeah, so that's what we got to investigate now. But I admit I could do B now, and if it came down to it, if I were writing the contest and I'd only gotten this far, I would write up, the 4s, like the zeros in the 1's digit, in the 4's digit, in the 10, in the 16's digit, in the 64's digit. The ones there will all eventually go away. All right. So the zeros in the 1's digit will go away. The 1s in the 4's digit will all go away. The ones in the 16's digit will all go away. And the ones in the... So everything else will work that way. But why? Why? Why can we keep going? Why does, if I add... So for example now, 31 is... f of 31 is 11, isn't it? If I add 16 to that, I will not get f of 11, but I think if I add 64 to that, I will. Will I? So let's go back for a second and look at the things that we did notice before. So we had 1 appeared when we... One seemed to appear when we did 1 plus any even power of 2. That looks like what we've got there. And then 3 appeared when we did 3 plus an even power of 2. Okay. So, 9 appeared there. And so when we did 4 more than 9, it sort of we did 4 more than 9, it sort of eliminated it, reset. When we hit the pass where we were doing the 4s, it got rid of the 13 that we had here. Right, because 13 is 9 plus 4. So I think when I made that guess, that I had something to the effect of, if x is less than 2 to the even, then f of x plus 2 to the even is equal to f of x. This is what I think we need to prove. I think this is the final statement that we would need to show. But why would that be true? So that's what we need to prove. I think this is true, and I think this gives us our answer, because there are infinitely more 2 to the evens more than 2005. Question is, why would this work? Okay, so I think now it's time to start trying to write some stuff up. So consider the numbers written in binary. I.e., 1 is 1 base with a little 2. You usually put the little 2, the little base, whatever you're looking at. 2 is 1, 0 base 2. 3 is 1, 1 base 2. And, for example, 15 is 1, 1, 1, 1 base 2. Okay. We claim the following. If f of n is written in binary, which is the same as base 2, then the ones digit cannot be 0, and the 2 to the k's digit cannot be 1 for any even k. If we prove this, so we'll say, if we prove this, then we conclude f of n will never be equal to 2005. Since 2005, and now I have to write it in binary, it's odd. That's not particularly helpful. 1024, and then we'll have a 5. It's probably easiest just to grab my calculator. Calculators are allowed, why not use them? So 1024, we subtract that off, we're left with 981. Subtract off 512. We get 469. Then the next one is 256. And we're left with 213, which is bigger than 128. And we get 85, which is bigger than 64. And then we get 21, which is less than 32. But then 16. And then we get 8, 4, because we get 5, and then 1, 0. Okay. Since this has a 1 in its, so 2 it's got a 1 in its 4's digit. And 4 is 2 to an even power. So it stumbles right off the block there. I thought we were going to have to go up to one of these other ones up here, but no. The 4 right there messes it up entirely. Okay. So, if we can prove this, we're all set. So I'm going to... I mean, you don't really need to show that the 1's digit cannot be 0. I'm just including this for fun. In fact, I'll even say... So it is clear that the 1's digit cannot be 0, as the even numbers are closed on the first pass. Alright. On the kth pass, every other locker left is closed. So every other locker, we'll have to note in a moment after the first. But on the kth pass, every other locker left open is closed. Okay, so we claim that all these lockers have the same 2 to the k minus 1 digit. Okay, this will be true for everything. We could prove it by induction, I guess. We'll do a really sketchy induction, but actually, what would be the best way to write this? My program's spazzing out again. So I don't feel like we've done enough work to just be able to say this is true, but we want to do a little. Yeah, I think saying proving it by induction is a little bold, so I wasn't going to really be that formal with the induction, but we sketch a proof by induction is fine, I guess. What do we want to say? I might just say something like, it is clear. I hate using the phrase, it is clear, but it is clear on the first pass on the next pass, we'll close every fourth locker. Not every fourth locker, but on the next pass. The difference between closed lockers is 4. On the next, the difference is 8. So on the kth pass, the difference between the lockers we close is 2 to the k. So the 2k minus 1 digit doesn't change between these lockers. Is that clear? Yeah. But the 2 to the k digit does. Okay. And in fact, not only does the 2 to the k minus 1 digit not change, but really the entire first little bit doesn't change. And I think that might even be a better way to do it. So the 2 to the k digit, everything before it won't change between lockers that we close on the kth pass. So I'll even add that little bit in case we need it later. Indeed, the lockers on the kth pass, the lockers we close, on the kth pass, all share the same first k digits, right? Because we start with 2 to the 0, so it'll be all the way up to 2 to the k minus 1. That's 0 to 3 is 4 numbers. 0 to 4 is 5 numbers, that sort of thing. So it is the first k digits. That might be useful later on. Anyway. On the first pass, we start from the left. So the increasing n, or increasing locker numbers. And on every odd pass, the numbers are increasing. Okay. So this is not hard to see. Again, I would say you could even say it is clear just from the picture that we've got going on here. So on every odd pass, these numbers are increasing. So now what do we want to say? So for an odd pass, we know the binary digits will alternate in the 2 to the k position. So what do we want to do here? Now we just need to justify why, if we're approaching, there's got to be one that's got a 0 in the 2k position that we skip over. So what do? We claim the first open locker has 0 in the 2. So for on every k equals odd pass, I think I'm getting my k mixed up. So we'll alternate in the k plus 1 position. So we claim the first open locker has a 0 in the 2 to the k. So k minus 1. So we'll say we claim it has a 0 in the 2 to the k minus 1 position. Right, so on the third pass, we care about the 2 to the 2, so the 4's position. Okay, so our numbers are matching up the proper way. Excepting on the first pass. We will not eliminate. I keep saying eliminate. We will close so we will close the lockers with 1 into the 2k minus 1 position. Right? Does this track with the way I was lining up the numbers this time? Yeah, the digit won't change with the ones that we close. So yeah, if we close a 0, so if we don't close the 0, we'll have to close a 1, and then it'll be 1 from then on. Okay, yes, clear. So we claim the first open locker has a 0. This will give us what's left over. Why does the first open locker a 0 from this point? Why? Also, this is taking me a long time, I feel, and I have to think that there's probably a faster way to do this. I just can't think of what it is. Probably some better trick with the binary than what I'm doing. Okay. So, you have a 0 in the 2k minus 1 position. Matter of fact, we can go a little further and say it suffices to show the open locker will be locker M with M less than 2 to the k minus 1. And that would be fine to show. Okay. So on each pass, half the lockers remaining are closed. Incidentally, it's half rounded down. Okay. So, and since it's every other one, so on the first pass, the number of lockers less than 2 to the k minus 1 that are left is 2 to the k minus 2. On next pass, this is at least 2 to the k minus 3 lockers are left. So on the 2 to the, or sorry, on the k minus first pass, we are left with 2 to the k minus 1 minus k minus 1, 2 to the 0 equals 1, locker less than 2 to the k minus 1. So since it's exactly one locker less, so the first locker on our first pass, since we're increasing, we have one locker with the 0 and then the next with the 0. The next one will have a 1 there. So this locker will be the one we skip. And the next locker will have a 1 in the 2 to the k minus 1 place, as desired. I think this could be a little cleaner, but everything that needs to be there is there. And based on our earlier comments about 2005, great, we're done B. Now it's on to C. So proving my x plus 2 to the even sort of claim. And I think that's true, but we're going to have to prove that. Okay. So this proves B. For C, we claim that f of x plus 2 to an even is equal to f of x if x is less than 2 to the even. Alright, so that's my claim. If this is true, so this would prove there are infinitely many n with f of n equal to f of 2005. Since there are infinitely many 2 to the even greater than 2005. So even if I was running out of time, I would still write this down. It does show why I would think this and why C should be solved this way, or why this does prove C. And the way marking schemes go, sometimes you get a mark for having done this conclusion bit. Yeah, we didn't prove the claim, but we do understand why the claim would work. Not always. I would say maybe 1 out of every 10 years, but still important to write down if you're running out of time. All right, now how do we prove this? Okay. I'm at a bit of a loss as to how to start this. Because while I'm sure it's true, I don't quite know where to go with this. And this is where it really makes me think that I have missed something crucial that actually makes this question a lot easier. While I'm sure this is true, I don't know how to prove it, and that's never a good sign. Because does that really mean that I'm sure that I know it's true? No, of course. If you can't prove it, you don't actually know it. So it's got to have something to do with the powers of, or not powers of 2, but sort of binary representations. It's got to be something with that. So actually, I think if x minus y is an even power, then I think f of x is f of y. And that would also prove it. And this is actually a stronger version of the previous thing we just saw. But why? So we go all the way up to x, and then we can go x plus 1, x plus 2, x plus 2 to the even, which is equal to y. And we sort of need to know that all these numbers here will be canceled out in a not particularly useful fashion. Alright, so the even ones would all be canceled out. So on second pass, so the pass that goes from right to left, the two to the one digit, the 2 to the 1's digit, so the 2's digit of the first locker we encounter will be 2 to the 2, or sorry, 2 to the even more than first locker we'd encounter that is less than X and left open. So they share the same 2 to the 1 digit. And so will f of x and f of y. Okay? Because sort of a rephrasing of some of the things we've seen before, I guess, which is probably a statement that should have been included earlier. F of n shares the 2 to the k minus 1 digit of first open locker, so not the one we close, on the kth pass. So if the first open locker we'd encounter coming this way, or the first open locker if we just cut off and gone this way, they'll have the same digit. Why? Because the one that's left open here and the one that's left open here, they will differ by 2 to the even. So they differ by more than by a power of 2 that's greater than the one that we're using to cut things out on this pass. And so since they share the same digit, they share the same digits as f of x and f of y by our little observation. Okay. So this statement isn't exactly true now, is it? You know, this one here, not exactly true, because otherwise f of 5 and f of 9 would be the same thing, and they're not. So it does have to be 2 to the even bigger than x. Okay. So since x is less than 2 to the even, this will hold true of the 2 to the k minus 1 digit on the kth pass for all k less than whatever even number. And what do I mean by this? I mean that the first open locker encountered will share the first open locker will share the 2k minus 1 digit with the first open locker encountered that is less than or equal to x. And so from there, so the first open locker encountered, well, y is so this shares same 2 to the k minus 1 digit with f of y, and the first one encountered that is less than x, it shares its 2 to the k digit with f of x, and so these guys share the same 2 to the k minus 1 digit. Alright. On the k equals our even digit pass, one thing I'm noting is I probably should have written this as like 2s or something. So on the 2 to the, on an even pass, actually no, that's it. We don't need any more of this. Right, I think that's it. So, So coming back, they're going to share the same digit up until, so the last pass is the 2 to the, okay, so we do need a bit more. So the k equals 2 to the s pass is the last pass. Again, since x is less than 2 to the 2s. And as we already noted, the first open locker will have a 0. Actually, it's this pass for all k less than or equal to. Yeah, so we'll have a 0 in the 2 to the 2s place. So it must be less than 2 to the 2s. And so we'll be less than or equal to x. And as noted above, so this already noted is the stuff we proved for part B. And as noted above, so in the blue stuff, we'll share this place digit with f of k. And since this is the last pass, f of x is f of y. Or f of y equals f of x. That was sloppy. But I think all the essentials are there. I'm actually going to go read their solution, because I feel like there was probably a slicker way to do it. But, yeah, I think everything was there. I don't think there's a logical gap. I think this is the least confident I've been on a Euclid 10 that I've done. But I think it's all there. Certainly f of 50, so we certainly did a part just fine. It's 33. But I'm fairly confident we got B part. C part is the one that I'm a little worried about with the logic, but I think it's there. I'm just going to talk it out verbally. So we noticed if you took an even part, like f of 9 is the same as f of 9 plus 16. And that should be the same as f of 9 plus 64. And maybe I should do that right now. But, so f of 73. I think to assuage my fear, I'm going to compute f of 73. I think that will put it to rest. Is what I'm saying happening? Because the first thing that we should encounter on each pass should be the same as the f of 9. Or it should have the same whatever's digit as the solution for f of 9. So for f of 9, the answer is 9. So this guy is 1, 0, 0, 1. Okay, so 17, 19, 21, 23, 25. I know I'm going to have to use multiple lines because we're going all the way up to 73. 37, 39, 41, 43, 45, 47, 49, 51, 53, 55, 57, 59, 61, 63, 65, 67, 69, 71, and our dear friend 73. So we passed through, now we're going back. We use the red, so we skip over 73. So he should be, so he has the same, he has 1, 0, 1, 0, 0, 1. So he does have the same, he has a 0 in the second on the 2's digit, yeah. And we cross out everyone who has a 0 on the 2's digit. Or no, it has a 1 on the 2's digit. Okay. And then on the way back, of course it'll have the same thing as the 9 because it's the exact same reasoning because it's the increasing version. So everything that's got a 1 in the 4's place will go away. Okay, and then we come back, and everything that's got a 1 in the 8's place, because that's what 73 has, will stay. And conveniently, that's what 9, well, not conveniently, mathematically, that's what 9 has. So a 1 in the 8th place goes away. Or sorry, a 1 in the 8th place gets to stay. 0 in the 8th place goes away. Alright, and then everything that's got a 0 in the 16's place will go away. or no, will stay. Jeez, I don't know why I keep saying it wrong. Then everything that's got a, so this has a 0 in the 32's place. Everything that's got a 1 in the 32's place goes away. Only one of those. And then on the last pass, we are increasing. So everything that's got a 0 in the 64's place gets to stay, and that eliminates 73. So it is, in fact, 9. So I am very confident now in our solution to see that as long as x is less than 2 to some even power 2 to the 2s, then x plus 2 to the 2s will be or f of x plus 2 to the 2s will be the same as f of x. So I'm much more confident because it has worked out the way I said it is. Maybe a little more justification is required, but honestly, they only give you so much space. They're looking for the highlights usually. So I think we got it. I think we definitely would have made it to the remark room. Then maybe our rigor would come under more scrutiny, and we would have gotten less marks. But there it is. So I'm much more confident. I'm glad I did that check. People watching to the end, that just made the video longer, so maybe you're not as glad. But there it is. That's the 2005 Euclid. More Euclids will be in the future, but I think next is we go all the way back down to a Gauss. So join me for more Waterloo contests, whatever they may be, the next Euclid, the next Hypatia, the next Pascal, who knows. But thank you guys for watching, and if you had a faster way to do this one, I would love to hear it or read it in the comments. I'm going to go check out their solutions, see how much detail they gave. But that's it. That's it for me. Thank you guys for watching. I'll see you next time.